Welcome back to Psych Bro, your go-to channel for mastering the Cambridge IGCSE Psychology 0266 syllabus. Today, we are exploring a highly biological topic, the role of the brain in memory and forgetting. Have you ever wondered where exactly your memories live in your head? Let's find out. We begin with a core concept called localization of function. Localization of function means that different brain areas carry out specific roles, rather than all areas sharing the same functions. When it comes to our memories, they are not processed by the whole brain equally. Instead, key regions, especially within the limbic system, are specialized for memory processes. How do we know this? Evidence for localization comes from brain scan studies. During these scans, participants complete memory tasks, allowing researchers to identify which specific brain areas become active. Additionally, post-mortem studies, which were used before brain imaging existed, provided evidence by linking specific memory problems to damage in particular brain regions. If multiple patients with similar memory deficits show damage in the exact same brain area, this strongly supports localization. So, where is the memory magic happening? Let's look at the limbic system. The limbic system is a network of structures located deep in the brain, beneath the cerebral cortex and near the brainstem. It plays a central role in emotion, memory, and learning. Two major memory-related structures within the limbic system are the amygdala and the hippocampus. Let's look at the first of these, the amygdala, which handles emotional memory. The amygdala is a small, almond-shaped structure located in the temporal lobe. It is responsible for processing emotional responses, especially fear and pleasure. Crucially for us, the amygdala strengthens memories that are emotionally charged. During emotional events, the amygdala is activated and releases stress hormones, which enhance memory consolidation. Because of this, emotionally intense memories are more vivid, more resistant to forgetting, and more easily recalled later. Research supports this. Brain scan studies show increased amygdala activity during emotional experiences, and stronger amygdala activation is linked to stronger long-term memory formation. Next is the hippocampus, the center for memory consolidation. The hippocampus is located in the inner temporal lobe and is curved in shape, often compared to a seahorse. Humans actually have two hippocampi, one in each hemisphere of the brain. Its key roles include organizing new memories, linking emotion to those memories, and handling spatial memory and navigation. Most importantly, it is responsible for consolidating memories from short-term memory into long-term memory. The hippocampus temporarily stores new information before transferring it to long-term storage elsewhere in the brain. It strengthens these memories by repeatedly reactivating neural circuits linked to the experience. By the way, sleep plays a vital role here. Memory consolidation mainly occurs during sleep, and different stages of sleep support different memory processes. But what happens if this area is damaged? Hippocampal damage can occur due to Alzheimer's disease, stroke, brain injury, or even severe stress and depression. The effects of this damage are profound. It can cause an inability to form new long-term memories, known as anterograde amnesia, and cause difficulty recalling recent memories. However, long-term memories formed before the damage are often preserved. This suggests the hippocampus is crucial for forming memories, not permanently storing them. Fortunately, the hippocampus is one of the few brain areas capable of producing new neurons, meaning recovery is sometimes possible. Memory rehabilitation strategies include cognitive exercises, brain-stimulating tasks like puzzles, and eating a healthy diet featuring fish and fruit. Now let's shift to the cerebellum, which is in charge of procedural memory. The cerebellum is located at the back of the brain, beneath the cerebrum and behind the brainstem. Though it accounts for around just 10% of brain volume, it contains over half of all our neurons. Its key functions include balance and posture, coordination of movement, and procedural memory, which is our memory for skills and habits. Procedural memories are formed through repetition and do not require conscious thought. Examples include riding a bicycle, writing, or tying your shoelaces. Repeated actions strengthen neural pathways, allowing these skills to become automatic. If the cerebellum is damaged, it can result in difficulty learning new motor skills, the loss of previously learned skills, and poor coordination and movement control. A massive piece of evidence for all this comes from the famous HM case study conducted by Milner et al. The aim of the study was to investigate the role of the hippocampus in memory formation. The participant was HM, a 41-year-old male from the USA suffering from severe epilepsy. For the procedure, HM underwent brain surgery to reduce his seizures, during which most of his hippocampus and amygdala were removed. Researchers then studied him in clinics and at home, and reviewed his earlier test results. The results were groundbreaking. HM maintained normal intelligence and could still recall his childhood memories. However, he could not form new long-term memories, meaning he suffered from severe anterograde amnesia. He showed some limited learning of simple tasks, but he did so very slowly and with errors. The conclusion drawn was that the hippocampus and amygdala are absolutely essential for consolidating new memories. Damage to these areas disrupts memory formation, but importantly, it does not disrupt general intelligence. Let's evaluate this biological approach, starting with the strengths. HM's memory impairment provides incredibly strong evidence for the role of these specific structures in memory consolidation. The complete inability to transfer information from short-term to long-term memory clearly highlights the hippocampus role. Furthermore, ongoing emotional memory research strongly supports the amygdala's involvement in strengthening memory. But there are criticisms and limitations to keep in mind. Memory is also linked to other brain areas, especially the cerebral cortex. The cortex processes information and supports higher cognitive functions. This suggests that memory is distributed across multiple brain regions and is not limited to the limbic system alone. Finally, how do we see the application of the brain's role in our everyday memory and forgetting? First, when we are learning skills, like cycling, we know it improves through repetition due to cerebellar involvement. Second, our highly emotional experiences are remembered much more vividly because of amygdala activation. And third, getting a good night's sleep actively enhances our learning by supporting hippocampal memory consolidation. That concludes our deep dive into the brain's role in memory. Remember to get plenty of sleep tonight to let your hippocampus consolidate everything you've just learned. This tutorial also marks the end of the first chapter. Drop a comment if you're struggling with a specific concept, and I'll jump in to help you out. Smash that like button if this helped, and subscribe to join the squad. Thanks for watching, and I'll see you in the next tutorial, in Chapter 2, Sleep and Dreaming.